Hello. For those who are not familiar with Idea Statica, it is a relatively new and revolutionary software that covers the design of steel connections according to the codes. It is based on finite element analysis, and it is the only software in the world right now to implement CBFEM method, which is the latest development in steel structural engineering. CBFEM allows total freedom in the geometry of the connection, on the contrary with traditional component method that has a lot of restrictions in the type of connections that we can design. For example, connections with hollow sections. In this video we would like to show you not only how we design a connection with Idea Statica, but the workflow that we can follow if we want to combine our main structural analysis software that is used for the global analysis of the structure. Of course, a steel connection can be very easily created within Idea Statica, but still it is very useful to import the connection from the main structural analysis software because we can also import automatically all the forces that are applied to the node. That allows us to save time, of course, and avoid also any typo mistakes when the input of loads is done manually. In this video, we will demonstrate through a real project the import of two connections from SCIA Engineer, which is one of the most known and advanced structural analysis software in the market. Of course, there are links to other software like Robot, Midas, RFEM and others, and more links to other software will be released in the future. So let's start from SCIA Engineer, and this is the project for which we want to design some connections. Although it is a simple structure, as you can see, the connections are a bit tricky because they are consisted of different types of cross-sections and especially hollow sections, which makes the connection a bit complex. So we're going to start the procedure, of course, by analyzing the structure. And especially for this project, this is also going to be analyzed with seismic loads. So the analysis has finished. And now we are ready to export the data of this project into Idea connection. So we're going to do that by XML input-output document. And we are exporting this XML. So the export has finished, and now we are ready to import this data into Idea Statica. So we are opening the application, and we're going to Beam tab, and here we can see all the different software that we can use for the import. So we're going to SCIA and select the file that we have exported earlier. So all the elements are imported, including the internal forces. And we can see the structure as it has been imported, so we can visualize it as 3D solids. So you can see that it is exactly the same structure that we had earlier in SCIA Engineer. In the bottom of the screen we can see a table that contains information about all the different members. So we can see here on the left the cross-section that it has been used, the length and everything. So for the design of the connections, we are going to connection design and joints. And I'm going to deselect all solids so that we have a better visualization of the nodes that have been imported. And now we can make a selection of the nodes that we want to design in idea connection. So for this example, I will choose two nodes. So I'm going to New, and I'm going to choose this one and this one. So I'm click OK. And now you can see that these two nodes are visualized in a larger sphere so that we can identify easily what are the nodes that we have selected. Here on the bottom of the screen, we also have some information regarding the members that are connected to that node. And we are able to edit this information so that we can include or exclude members. So in our example, I would leave the Ni N50 node as it is. And I'm going to edit the second one so that it includes also the column. So I'm going to select from the available members, and I'm going to move this to selected members. In this screen, we also have the possibility to define some members as continuous member, which is the case in our example here because the column is a continuous member. So I'm going to select this option here, click OK. And now we are ready to design these two connections. So I'm going to click Design and save this as a file. So what happens is idea connection opens automatically, and it will contain both connections, both nodes that we have selected. So as you can see here, we have two. This is the first one and the second one. You can also see that all these arrows represent the forces that have been imported from SCIA Engineer. So let's start by designing the first connection. So I'm going to Geometry, and first of all we need to make some adjustments to the geometry, because as you can see there are some things that are not represented well, and this is logical because the model has derived from a structural analysis software that uses an analytical model, so it creates the center line for all the beams. So we are going to make some adjustments in the geometry so that we can have the correct geometry as it is in reality. So first of all, we are going to change a little bit the height of the column. So now the column is aligned with the rest of the beams, as you can see. And now we can move forward and make some manufacturing operations, as we call them in idea connection, so that we can connect properly the beams to the column. So we are going to Design, and we add a new manufacturing operation, which in this case will be a stub plate-to-plate connection from the beam to the column. So we are choosing a bolt assembly, and now we have to change, of course, some things here. So we're going to choose a different member, which will be member 48. As you can see, the stub has moved in that element, and we also need to adjust the position of the stub. So we're going to put 300 millimeters. So as you can see, now we have a more correct geometry. So this is something that we can copy as an operation so that we don't have to do it again. So just copy it and use 49 as a member. that's it. Of course, there are a lot of adjustments that can be made here, so we can put additional bolts, or we can adjust the plates, make it bigger. So I'm not going to do that right now, just to save time. So I'm going to move to the next manufacturing operation, which will be the cutting of this member from the column. So I'm choosing additional cut, and of course I need to change the member, so I need to cut member 48 from member 4, which is the column. And I'm going to choose the cutting method as a surface. So you can see now that the beam is cut very well from the column. We can, of course, copy the same operation, and we can choose 49 as a member. So now we have both beams correctly cut by the column. And if I make the model transparent, you can also see that the welds are automatically created from the beam to the column, and they are represented with this red line. So the next thing is to adjust also the diagonal member here, and for this I'm going to choose a gusset plate. So I'm clicking a new manufacturing operation, which is gusset, and for that I'm going to choose member 62 and connect it with a new plate, and the member will be stub 1. So as you can see, the gusset plate is automatically aligned to the stub. Of course, when there are some small adjustments that needs to be made. For example, we can make the width 150 and the depth, let's say, 200, and we should move a little bit this gusset plate here, and I'm going to add a new manufacturing operation, which is the weld, because I need to weld also this side of the gusset plate to the column. So I'm going to add a new operation, which is the weld, and the weld will be plate. And as you can see, the gusset plate has some different edges, which is represented by an index. So I'm going to choose index number 2, which needs to be welded to the column. So now you see that a red line has appeared here, which represents the weld of the gusset plate to the column. So the final thing that I need to do is to adjust a little bit the length of this diagonal. So I'm going back to geometry, and I'm going to choose 62 and make it, let's say, 500 millimeters. And I think we're ready. The geometry is ready, and the only thing that we need to do right now is to analyze this connection. So to analyze it, I'm going to check and calculate. So as you can see, the calculation has finished, and we already have the results on our screen. We can see a summary of the results, so we can see that all loads have been applied to the connection, and we have also some results about the plates, the bolts, and the welds. So you can see that at the bolts we have a problem here, because some of the bolts are not passing the checks. What we can do here is we can visualize, of course, the meshing that has been automatically created by the software. And we can also see the bolt forces. Graphically, you see a green arrow that represents the bolt forces. We can also see the equivalent stress of this connection and the plastic strain. So you can see the areas that we have the higher plastic strain. Of course, all these results have to do with the analysis, and on the left part we have all the checks, the CBFEM method checks, which can be viewed if we click these two buttons, the stress check and the strain check. I'm not going to get into many details about the analysis results, since our main objective here is to cover the general workflow. So I'm going to move to the next connection that we have imported. So this is the N21 connection that we can see here. So I'm going to geometry, and first of all I will make some small adjustments to the length of the two diagonals. And I'm going to make them a little bit longer. So what are we going to do is that we are going to connect these two diagonals with the column with a gasset plate. So we are going to design, and we are entering a new manufacturing operation, which will be the gasset plate. So we're going to choose the DM22 member, and as you can see, we have already a gasset plate enabled. We can make the model transparent to see exactly the geometry of our model. So let's try to adjust a little bit the gasset plate. First of all, we need to apply a bigger width, so this is going to be 600 millimeters. The depth will be the same, and the position will be minus 140, so that the gasset plate is equally located between the diagonals. I will also make the gasset plate a little bit thinner so that we can visualize afterwards better the results. And I'm going to change also the position of the member. To 400 millimeters. So as you can see, it is almost at the corner of the gasset plate. But we see that the gasset plate, the corner is actually entering the member, so we are going to make some small adjustments there. And to do that, we are going to Editor and Gasset. And here we have the option to make a chamfer to the corners that we want. So in that case, it will be corner 2 and corner 3. And the value will be 30 millimeters. So our corners are chamfered now. So if I click OK, we will see that now the geometry is correct. we have no clashes between the gasset and the member. So let's move to the other member now, and to do that I'm just going to copy the same operation, but in that case I will choose 21 and not a new plate but an existing plate. So now we see that the two members are connected to the same gasset plate. Another small adjustment that we can make is that we can add the second bolt, a second row. And we can also change the type to a double plate. And we can also change a little bit the width. And it looks like this. So we can do the same adjustments to the other one as well. So 70 millimeters and a second row of bolts and a double plate. So I think we're ready. The geometry is perfect. So the next thing is that we can analyze this connection. In order to do that, we're going to check, and for this particular connection I will enable also the backlink analysis. As you can see here, we have the option to enable the backlink analysis as well. So I'm going to calculate, first of all, stress and strains. So we have the results. If we go to equivalent stress, we can see the stresses that appear on our model, on the members, on the plates, on the bolts. So everything has been analyzed. And we can also make visual the deformed shape of the connection. So if I click deform, we can see that we have a modification factor that shows us exactly how the connection is deformed with these forces. And this is something that we can also use during the backlink analysis, and this is very useful because it shows us exactly how the connection buckles. So we see that we have all the different results as well. So all the plates, we can have the bolts as well and see the forces, and of course the welds. So next thing is to do the backlink analysis. And since the backlink analysis has been completed, we have another button here that is active now, which is the backlink shape, and I can enable it so that we can visualize exactly where the backlink appears on our connection. So you see that the gasset plate is the most weak part of the connection. So through these two examples, you have seen how easy and straightforward is the workflow between the main structural analysis software, which is in this case was SCIA Engineer, and IDEA Connection. It allowed us to easily import all the geometry and the loads and prepare a very detailed model of the connection, which is then analyzed and checked according to the codes. Thank you for watching, and make sure you subscribe to our newsletter and our new YouTube channel for more videos that will be released in the future. Thank you.